Okay, so as a reminder, the vapor pressure is sort of like the boiling pressure. If the pressure is, if the vapor pressure of a liquid is, for example, 2 atmosphere, and right now we obviously live at 1 atmosphere. If I changed the conditions around me to 2 atmosphere, the liquid will boil. So it's just like temperature, just in pressure, and from a pressure perspective. How can I boil my liquid? By applying pressure, not temperature. So what it turns out that the vapor pressure of a liquid, right, can be reduced by adding something to it. It's just like a freezing point depression here, but now it's a vapor pressure depression. And the relation here to tell you what that is that the reduced pressure, the one that in the mixture, the pressure of the solution, okay, is equal to X, which is the mole fraction of the solvent, times the pressure, the vapor pressure of the solvent, if it was by itself pure. Okay, and I'll show you an example, so don't worry about that. But the rationale here again is if I have the pure stuff, sort of like the boiling point, just like we had before, the freezing point we had before. Say it was 0 degrees Celsius for water. If I add something to the water, I get to multiply it by a mole fraction of the water, and I'll get the reduced freezing point as a result of the solution. Okay, it's very similar. But in here, we just talked about the delta T, not the actual temperature that you would actually see, which is fine. It's just very similar. This equation is known as Raoult's Law, and it is used quite extensively when discussing solution thermodynamics. Okay, so let's look at an example. So in our example here, we have the vapor pressure of water, the pure vapor pressure of water, is 0.0313 atm. And I want to know if I were to add salt to water, in this proportion, I have 2 moles of salt and 10 moles of water, what's my new vapor pressure of water? And this is Raoult's Law. Whenever you see vapor pressure being reduced, it's Raoult's Law. So the pressure of water in a solution is going to equal to the X of water, it's the X of the solvent, times the vapor pressure of water, and this little O at the top means that it's pure. Okay, so now you can kind of see it in action. The pure vapor pressure is given to you right there, so that's that. And the mole fraction, you can calculate from these 2 moles, we'll do that in a second, and then you get this. That's what I'm asking for. Determine the vapor pressure of water in solution. That. So how do I do this? Well, this is equal to mole fraction, which is the mole of water divided by the mole of whatever's in there, of the whole thing. So moles of water plus the moles of salt. That's what I have. And so mole of water is 10, and of salt is 2. And so I get that my X of water is equal to 0.167. It has no units because mole divided by mole goes away. And so now I have X, and so that goes in there. Perfect. So I have the pressure and I have the X, and so I can just apply Raoult's Law, and my water has a new vapor pressure equaling to 0.167 times the pure one, which is 0.0313 atm, and the solution at the end has the same unit, so it will be 0.00522 atm. Okay, we can look at another example that's a little bit more complicated than this. So the pure vapor pressure for water is given to you here. And what is the vapor pressure if I'm mixing into water two solutes? Okay, so again, I'm going to use my Raoult's law. So my new vapor pressure for water is equal to the mole fraction of water times the pure vapor pressure for water, like this. And this is given to us as 17.5, so that's nice. That's good. And we're looking for this. This is a reminder, this is all we're going to do. It's the mole of water divided by the mole of water plus the moles of CONH22 plus mole of C12H22O11. Okay, it's just annoying because we were given different units. This is in grams, this is in grams, this is in moles. Okay, so at least this one is in moles, so we don't have to deal with it. But the mole of water we need to figure out, and the mole of urea. So let's do those, and then we'll put them back into here, and we'll be able to get our X. This is X water. Moles for water. To get this, I have 1,000 grams of H2O and 18 grams per mole of water, and that gives me 55.56 moles of water. And then mole of urea. Again, it's the same idea. I have 75 grams of that. And then if you go look up in the periodic table and figure that out, you see that it's 60.1 grams per mole. And so this ends up being 1.25 moles of urea, which is CONH22. Okay. So we have the moles of urea, we have the mole of water, and the mole of sucrose we were given, which is equal to 0.250. Okay, so now we can figure out X. Okay, let's go down. X now, X for water, is equal to 55.56 moles of water divided by 55.56 plus 1.25 plus 0.250 moles, and this entire X ends up being 0.974 as the mole fraction of water. So now we're ready to put that back into our Raoult's law. To remind you, we have this, we didn't have this, and we want this. So now we have it all, so let's put it in. So this ends up being 0.974, as we just calculated, times P of water, which is 17.5 torr. And so our final answer should be 17.1 torr. That's our new vapor pressure.